Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. In today's session we are going to discuss on interference or a shrink fit in a Abaqus Standard implicit solver. So right now on my screen what you see is a typical interference or shrink fit problem. A solid shaft where you have a bronze or brass bushing fit using an interference fit on a shaft. So the middle portion, which is a solid shaft 50 millimeter diameter, since it is a solid shaft we have model as a rigid, and there is an interference fit between a bushing which is a brass bushing on a shaft, and there is a 0.3 millimeter across the diameter. There is an interference, and now you see because of interference slowly interference is getting out, and then bronze is going to fit on a shaft. So before going to this problem definition, we'll quickly touch what is a problem, how we are going to solve it, what particular approach we are going to take it. So this particular problem we are going to solve in a Abaqus implicit Abaqus Standard, and is a shrink fit simulation. So interference fit, generally a lot of mechanical fit between a shaft or bearing or shaft with a bushing is done using a interference fit, and most of the time the shaft are steel or any other material, and the bushing or the bearing metal is most of the time is a soft metal like a brass, bronze or gunmetal. And there are a lot of calculation involved in a shrink fit. What should be the inner body diameter, what should be the outer body diameter, which metal we should select, how much should be the shrinkage fit, or some bond or shrink fit where you actually apply a temperature. So they are shrink fit, but they also get heated the outer outer brass bearing. So there are a lot of design consideration going on, and then Abaqus Standard have this option for a contact interference. So we are going to solve this problem where shaft is 50 millimeter diameter, its length is 100 millimeter, and over there is a bush of a brass or bronze bush which is a 20 millimeter in the width, and the inner diameter is a 49.8. So there is around 0.3 millimeter 0.3 millimeter is a interference there, and then outer diameter is 100 millimeter. So this is problem we are going to solve, and there are a lot of softwares available online where actually people do this type of interference fit, and then they predict what is some level of calculation of a contact pressure, then how is the stresses generated in inner member and outer member. So this all these question, this answer to this question you can get into Abaqus. So just again starting this problem, we'll just quickly go through what is the interference fit. And this is, if you do a googling, you will find a lot of things is like a press fit or a friction fit, which is actually two parts is pushed together using a friction. And then there are a lot of design consideration. What I mentioned is a tensile and compressive strength of the part, how much should be the interference fit, what are the stresses generated, what is the contact pressure, contact forces generated because of this. And typical examples are like a press fit shafts into bearing or the bearing houses, and watertight containers to the cable. So we are going to solve this problem in a Abaqus Standard. So preprocessor we are going to use a Hypermesh, and the typical. So here I define steps. So we'll create a geometry, shaft geometry, bushing geometry, metal property, will assign property, we'll do mesh creation, and then we'll get into a contact definition where we'll create a surface, then we'll define the contact, interference fit, and then boundary condition, and then we'll get into a step creation, non-linear static steps, and then we'll run it and see how this. So major takeaway this is actually we'll able to do this using a contact pair. So you'll learn how to define a contact pair, and then how to do a contact interference like a star contact interference, shrink fit type contact pair. So let's get started. So we are going to start in Hypermesh as a preprocessor. solver will be Abaqus Standard implicit solver. So there is nothing on my screen right now, so I just select a particular view here, and I'll just using F8, which is a node creation. I'll just create a center node. So this is my center node as 0 0 0 coordinate, and I'll first create a shaft geometry. So I'll create a shaft geometry. I'll select some color, and then I'll say create and line, and then I'll select this, and then I'll say 25. So this is a 25 radius, so 50 millimeter diameter shaft geometry. Then I create one more component. So you go here is a component, and then I'll say bushing geometry. I'll select, say, something like a blue color, and then I'll select this, and then it is a 24.7. so there is a 0.3 interference there, and then I'll just create outer diameter, which is a 50 millimeter radius. So that's what actually we created, just a cross section we have created, shaft cross section. We have also created cross section for bushing, and right now I'll just go back for just a fraction of second to a problem definition. Now if you see this problem, this is actually quite a bit symmetry advantage we can take. So we can model this as a 1/4, or I'll say we can model this as a 1/8 model. So if we model this 1/8, so we can take the advantage of symmetry and then put a symmetry boundary condition and reduce the run time. So we are going to do a 1/8 model. So first we'll then modify this. So we already created the 2 diameters, so I'll just create a F8 again, and then I'll just put on this particular line around 5 node, and then I'll just create an additional line here. So again this I'm doing because then I can just cut this into quarter. So I'll say line edit, and then I'll select this line, and then this is cutting edge, so it is cut. So again I'll say other one, and then I'll say this is cutting edge, so this is cut. So now if you see there are 2 cutting edge. Now I'll say bushing shell. So this is like a shell element I'm going to create. So this shell will be, then we can extrude it. So our strategy will model a shell, and then we'll extrude in perpendicular to this plane for 10 millimeter, because 20 millimeter is the width of the bushing. So we'll just 1/8 model, so we'll just drag it by 10 millimeter. Then we'll say 2D, and then we'll say ruled, create, and then I'll put something like 0.7 here, or something like a 1 millimeter. So this is 1 millimeter, and then I'll use a biasing here. So around 50% biasing I'll do, 70% biasing I'll do. So we will get a more refined mesh in here, contact region, and then bit of coarse mesh outside. So that's what actually we done refining. So this is how you can see a 2D mesh, how it looks. Then I'll just create a bushing solid, and then I'll select some color. So I'll select this color, and then I'll say 3D drag element. I'll select by collector, and I'll just drag a 10 millimeter, and I'll say I want a 10. So drag by 10 millimeter, and then I say 10 elements on this. So this is my 1/8 model of bushing is created. Now I'll just switch off this, and I'll switch on a shaft geometry. So I'll just from here I'll just go to shaft geometry collector. I'll also create a couple of lines here just for a cutting purpose. So once I cut it, then I can use that. So these lines are not created exactly where actually I want, so I'm deleting. So I create a 5 on this, and then I can just create a line between these two diametric end, and I'll say line edit, and then I'll select this, and then I'll say cutting edge this. So I created a quarter section there. Now I'll say shaft shell. Now since it is a solid shaft, we know it will be having a infinite stiffness. It's a quite high stiffness compared to bushing because of steel. So we are going to model this as a rigid component. So I'll select some color, and then I'll say wow, 2D drag. This will be 2D drag. I'm going to drag this geometry. So I'll select this Y, and distance will be like 100 because it's a 1/8 model we are going to do. So just this section, and then 100 total is the 200. So it's bit coarse mesh here, so I'll put around 2. So you can see this is actually a mesh of a shaft. So we have done that. So now you see this is a solid gunmetal bushing, and then you have a rigid shaft here, and then you can see here there is an interference here between the two. So since now we have done a modeling, so I'll just go back what position we are there. So we've done a mesh creation. Now we'll just create a metal property, and then we'll assign a property to this. So material will create a bronze, and we'll give just elastic modulus, so it's a 100 GPa, and then the Poisson's ratio is 0.34. it's a bit higher compared to the steel. If you have plasticity data, you can put a plasticity data here also, which will be much good. Then you can see how much plasticity generated in interference shrink fit region. I'll quickly create a bushing name I'll give, and then I'll say a solid section. I'll say solid section, and then metal property bronze. So this is now solid section bronze is created. So I'll just select that solid bushing component, and just I'll update with a property of bushing. Now this is up to date. Now it have section assigned, which is a solid section, and also materials assigned. For shaft it is a rigid, so we didn't require any material. So rigid, I'll select a rigid section, rigid body, then we don't require any material, and then I'll select some. So I select this component, so it is star rigid body, shaft shell is already selected, and this will be my reference node. So this is my reference node where I can put a boundary condition which will be applicable to the all nodes. So that's it. Now we almost created bushing, and we have created the shaft. We are also given a metal property, everything. Now I'll just delete which is not required. So let me first save it. So save contact interference demo. So I save the file. Now I'll delete what is unwanted. So something like a bushing shell I don't require. So I'll say element by collector. I'll just delete it. I'll delete empty also. So now I'll just quickly put a boundary condition. So analysis, I'll just create one collector. So next to property, you see a load collector where I'll say rigid BCs. I don't want a card, anything, no card. I'll select something and I'll say analysis constraint, and I'll just select that reference node, and then I'll just create. So I'll just quickly check whether that reference node is correct or not. So it is, we have selected the right node. It is very important to actually put a boundary condition on reference node. In case you are not put on reference node somewhere else, then that boundary condition is not applicable to rigid section. Now the other thing we have to do is we have to put more like we have to really put this symmetry boundary condition. So we'll quickly create a node set. So I'll just again put in one particular section. So this is a Y symmetry, this is a Z symmetry. So we'll create a node. So entity set, I'll say first Y symmetry. I'll select nodes on, I'll first select a Z symmetry. Z symmetry, nodes on plane on Z axis, and then I'll select this and I'll say create. So Z symmetry node sets are created. Then I'll say X symmetry, nodes on plane X. Now I'll just select this face, which will be a Y symmetry. So let me first check how is the sharp oriented. So this all nodes are a Y symmetry. So nodes on plane. So now we also created all this node set for boundary condition. Now we'll quickly put a contact pair. So first shaft, let me see how is the orientation and how far we want to generate a contact element. So somewhere till we'll generate a contact element till here. So I just took some reference node there, put some temporary node to where I have to put, and then I'll say I'll check normals. So shift F10 if you do, you'll see a normal, and there you'll find a panel where you can get this normal. Actually I'm from the old simulation school, so I use all this shortcut. So this is actually outer normal. So I'll create a master. So I'll just put in some view interface. I'll just create master. Master surface will be all the time is a rigid surface. So create, and then I'll say add, and then I'll just select all this. So this is my master surface. In case you want to have a detailed understanding which should be the master, which should be the slave, our contact overview videos is there uploaded in YouTube. You can have a look into that, so you'll get a better idea how we have to select master and slave. Then for the solid element, we'll take a face. So you go to tool, say face, and then you select a component, select, and you just find a face. Then you put a display option D, you say none, you just take a face, and then you select analysis, you go to interface, and then you put a slave, you give some color and say add. So you add that, so you'll see a slave node. Again go to tool, faces, and delete the faces. Now guys, you have all groups, both master and slave surface, so the only thing missing is a friction. So you go to again a property card, you put a friction there, then you see a interface properties, and then you select friction surface property, surface interaction, and say create and edit. So you'll find a friction there. So surface interaction, so I'm going to put here 0.2 generic friction value. Now why 0.2? Because the shaft and bearing will be a bronze or gunmetal, so it will be smooth, lot of tolerance and surface finish are there, so the friction will be on quite lower side. Then I'll again go to analysis interface, I'll say contact pair, and then you put a contact pair here, you create and edit, you select that friction property, you give slave, you select a master. Now this is a normal thing what we do. We define now a contact pair master slave. Now how to define there is already interference, so you go to intersection and then you define a contact interference here. Then you select this contact interference card type and then say create and edit. So you have different options here. Contact interference, you can give master slave, you can give an interference value. So we'll give type, will give contact pair, so we'll define a contact pair and we'll say shrink fit. So it will be star contact interference shrink type contact pair. Then you select what is a slave and then master. Now how much is the penetration? So based on that shrink fit it is calculated and it will remove that penetration. So let me save it again. So we define now, we mesh it, we define contact, everything. Now I to just put this symmetry boundary condition. Now symmetry boundary condition, like if it is symmetry about x, then you have to constrain the x displacement and y and z rotation. But since it is a solid element, you will not have a rotation, so we are going to just put a, if it is x symmetry, we are going to just constrain the x displacement. If it is a z symmetry, we are going to just constrain the z symmetry. Now I'll just again go to load collector and I'll say symmetry BCs, then it will be initial condition we can put, so it will be before the step. It can be a initial or it can be history, so only the advantage is initial will be is before the step. Then you say boundary condition and then I'll say 3 different sets. So first one is x symmetry, second one is a y symmetry, and third one is a z symmetry. So for x symmetry, x displacement constraint, since there is no rotation y and z, so we are not going to put that. Y symmetry and then z symmetry. So you are done with that. So now we have created all the boundary condition, everything. So I'll just quickly go back to the steps. So we have also generated analytical surface, contact definition, boundary condition. So step creation will go. So before going to step creation, make sure you select the appropriate element for the shaft, which is a rigid section, and then appropriate solid element for the bushing. So 2D, I'm going to element type, I'm going to select R3D3 or R3D3 or R3D4 rigid element for shaft, which I selected, and then for bushing, which is a solid element, I'm going to use a C3D8 continuum 3D8 noded incompatible mode element I want to choose, because incompatible mode you have some advantage with that. So we'll have that session somewhere later. So I just updated proper element. Now you go to analysis. Now before creating all steps, we'll just create output block. So in output block, we'll ask for a output field variable, frequency as 1, and variable is equal to pre-select. We'll select a node output, we'll select a element output, and then possibly we can have a contact print in case we want to see diagnose how this is working. So contact print also we have put contact print for every one frequency. So we've done that. Now we'll just go to the load step. We'll say interference, then we'll go to load corrector, rigid, symmetry, boundary condition. We'll select out block, and this is very important, guys. Now in groups you have to select this contact interference. It will be inside the step, so there will be a contact pair defined outside, and then there is a contact interference defined inside the step. So you say create and edit. So stars, you select it as a static step, you select other parameter, NLGeom is on, and then you select a data line. Will start with very small time period t1. So actually it will over a period of all these time increment, it will remove the penetration. Then you see this boundary condition. Then important thing is a contact interference inside these steps. So now it is ready to go. I'll just save it, demo model. I'll just export it and demo model, and then we can have also a check into we'll check into a text pad how this looks like file. So INP, so export. So in text part we'll search what are the different are there. So it is a node, then you have R3D4 shaft element, C3D8I bushing element, then you see a reference node, ZXYZ symmetry, bronze property, friction value, you define a contact pair, then you have this symmetric boundary condition, then rigid boundary condition is there also, then you have contact interference. So I think it is ready to go. Let's run it. So I'm going to use, so this is like Abaqus 6.1133. so I'll say Abaqus 6113 job is equal to, and I'll just copy the job name, and then I'll say CPUs is equal to 8 CPUs I'm going to use. It's depend, if you want to run with single CPU it's fine, or 2 CPU. So because I have some tokens available, so I'm running with 8 CPU. So it just run started. So it's going to a pre.exe. So it's checking whether there is any preprocessor related error. Then it could, if there is no preprocessor related error, now it's gone to standard. Now we'll just wait how this is going to converge. So once we get a converged result, we can just discuss on that. So just wait for the model results. So guys, run is done. Results are also got converged. I just open a STA file, and then you can see some severe discontinued iteration, but it's gone very smooth. I also load the results here in Abaqus viewer 6.1133. so when you load the results, it will be like a 1.8 model. So you go to view and then ODB display option, and then you select mirror whatever, all XY, YZ and XZ plane, and then you model a full, and that's what actually you see on the screen. Now it is removed all the whatever was interference which was removed, and then you can look into different parameter like a contact pressure, how much is the reaction force generated on the shaft, the stresses is tensile or not. So everything related to interference feed design, you can do it. So the major learning, actually what actually we want to share with you as a Abaqus user, how to do interference feed. So you have major option like in interference feed is use a star contact interference comma shrink using contact pair. So it is very straightforward. You define a contact pair, you also do some engineering judgment on if you take advantage of symmetry, then if shaft is solid, then you put that as a rigid consideration, and then major thing is you define two contact pair, then using a star contact interference shrink type is equal to contact pair, you can solve this contacted interference problem. And then there are the other options also which you can explore in terms of amplitude you can give. So guys, I think this is I guess it will be useful for us, for you. So go ahead and start exploring a contact interference fit in a Abaqus Standard implicit solver. In case you have any question or doubt, please email us at the abaqusacumen@gmail.com. And one important thing guys, this is actually a non-profit project which we are doing for Abaqus community. So don't forget to like us, give valuable feedback, and don't forget to subscribe us. Thank you. Bye bye.
Yeah.